Today, we're going to possibly finish up talking about volumes of solids of revolution, wherein we find the volume of a solid formed by rotating a region about an axis. The fun part that the fun challenge that we've issued ourselves is that we only get to use one variable because we're in single variable calculus. It's like when you're playing an open world game and you decide you're only going to use the telekinesis spell. So it's not a necessary part of the challenge. It's just like, but it makes it more interesting. It's a little bit necessary for us because we're in single variable calculus. And so we kind of have to set everything up with a single variable because that's all we know how to deal with at this point, secretly. But the big idea is that integration is multiplication in which one of the factors is variable. The single variable restriction means that it only gets to vary in one way. So when we say the volume of a solid, a volume is cross-sectional area multiplied by height, the cross-sectional area has to be variable with respect to the height. So at different heights, we have a different cross-sectional area. And so what that forces on us is that the cross-sectional area does have to be constant in its shape. So the cross-sectional area must be constant in shape. It has to have a constant shape so that we can write everything in terms of one variable, but it can vary in size. But because we're in single variable calculus, we have to be able to express the size as a function of the height. Or whatever variable we're using to represent a change in height. So there are still, these are the restrictions that we put on ourselves because we're using a single variable. So what I mean by that is if I have, let's say, a plate, what I mean by vary in one direction. So I actually didn't want to draw a rectangle. If I have a shape, I'm going to use the one from yesterday. We have this parabolic shape. So the area, if we want to imagine the area as length times width, if we want to imagine the area is length times width, then we can draw a slice this way, and we can talk about the width. Come on, Ben, get going. And we can do this in a couple of different ways. We slice this area horizontally, or we could slice it vertically into, but it's always sliced into rectangles because that's all we need for area, length times width. So we have these choices that we can make because we're just finding area. One of them takes place of the delta x, the other is the delta y. So what I mean is that we have to choose one of these directions to be the variable direction. We have to choose the delta x direction or the delta y direction. So if there's some other quantity that's being variable, so if, let's say, the density of the region was a function of x, now I can't choose the delta y variable. I have to choose the delta x variable. If the density varies side to side, then I have to use the delta x formulation for the area. So if I wanted to calculate mass is density times area, if the density is also variable and varies with x, then I have to choose delta x. I can't vary the area with a delta y while the density is variable delta x. We have to slice where things are constant. And if density varies with x and I slice horizontally, then the density is variable all the way through the slice. And since we only get one variable, we can't do that. So if density changes with x, then we have to choose the delta x for the area. Because we only get one variable, I can't vary the density in the x direction and the area in the y direction. Since we only have one variable, we can't vary the density in the x direction. And area in the y direction. This is the restriction that we placed on ourselves at the beginning when we decided to play the single variable calculus game. This is the reason. This is because we're playing the one variable, single variable calculus game. And we reserve multivariable calculus for Calc 3. Here's the fun part of switching from single variable calculus to multivariable calculus. When you switch to multivariable calculus, you already know what you need to know. You already know how to find antiderivatives. You already know what the definite integral is supposed to represent. We're just doing this with functions of more than one variable. We have to upgrade our language a little bit. Like when we talk about the derivative as the instantaneous rate of change, we can stop right there because there's only one direction in single variable calculus. It's the rate of change of y with respect to x. It's how the function is changing in the x direction. So it's the instantaneous rate of change with respect to x. If I have a function of more than one variable, I could look at the instantaneous rate of change with respect to x and also with respect to y. So I can just look at more derivatives, and I just have to be specific about which derivative we're talking about. So when you get to multivariable calculus, always remember that you know how to you understand the calculus concepts. What you're working on is looking at functions of more than one variable. That's the thing that you're adding to it. This is the same way that I look at algebra as it relates to arithmetic. When you get into algebra, I think the thing that we should have emphasized, I don't know if it was with you, because I don't know what your algebra history was, but what we should emphasize is that algebra is not a new thing. You already know how to do all the process in algebra because you learn those things in arithmetic. And if we learned arithmetic properly, then we're just upgrading it to fit algebra. So if we learn single variable calculus properly, which is always a gamble if you're in my class, then when you get to multivariable calculus, it shouldn't be that big of a leap. The calculus ideas are still in play. The infinity ideas are still in play. We're just dealing with functions of more than one variable. And that is why I emphasize things so much when we talk about integration. I think of integration as multiplication, in which one of the factors is variable. Integration is just addition. So this is why I focus less on, I focus so much on saying those things over and over again. Integration is multiplication, in which one of the factors is variable. Integration is just addition. And when we talk about these slicing problems is we slice where things are constant. When I say if density changes in the x direction, then we must use the delta x for area as well. So if the density is varying in the x direction, I can't use this delta y slice because the density is not constant throughout that whole slice. But if the density is varying in the x direction, the density is constant at this slice. It changes a little bit with the delta x, but if delta x is small enough, it doesn't change that much. So this is why I also keep repeating the thing, we slice where things are constant. I want to bring this up again today because we got bogged down in a lot of details this week where we're doing a lot of analytic geometry. But now we've got all that sorted out. We've got our strategy for slicing parallel to the axis of rotation and slicing perpendicular to the axis of rotation. It either makes discs or washers or cylindrical shells. So now we just need to practice filling in those blanks. Any questions? I didn't intend for that to happen, but one of my favorite things has happened. I just mentioned that you know how to do multivariable calculus already. So we know that if we have a function of x, let's say f of x is 5x to the third. We know we can take a derivative, f prime of x, and that's just 15x to the second. So you know how to take derivatives. Let's suppose that we have a function of two variables. We have two variables, so we can calculate the slope in two different directions, one in the x direction and one in the y direction. So we could take the derivative of f with respect to x. So I can't use this prime because prime is not variable specific. So here's what we do. We just write a subscript. Take a moment, and I'm going to give you a few, like 15 seconds to guess what the derivative of this function with respect to x is. Just the x direction. Don't worry about where y is going. So if you're having trouble thinking about it, I just said calculate how f is changing in the x direction. don't worry about what y is doing. Keep y constant and just look at what's happening in the x direction. And when I say keep y constant, that should trigger us to say 15x squared. Keep y constant, you say? Okay, it's still y squared. But this is a function of two variables, so there should also be a derivative in the y direction. And I'll say the same thing. Look at how things are changing in the y direction. Don't worry about what's happening with the x. That is, keep x constant. So what's the derivative? Not just 2y. 5x cubed is part of that constant. So the derivative is going to be 10x cubed y. So there's the 2y, but 5x to the third, we're just keeping that constant too. Like I said, you already know the process. You already know the calculus. If we understand the thinking and what these things represent, and they're not just automatic processes that we're trying to program into you, then moving forward, it's just a small adjustment to capture new ideas. This is the power of understanding what's going on and not just being able to do what's going on. Any questions? It gets even better. When I look at a function y equals f of x, it's a one-dimensional curve in two-dimensional space. So the graph of y equals f of x is a one-dimensional curve in two-dimensional space. It's in two-dimensional space because there's only two variables, x and y. So that defines the space. It's a one-dimensional curve because it's a function of just one variable. There's right and left on this thing, and then that's it. So if I up this to a function of two variables, well, it's a function of two variables, so it's going to be a two-dimensional thing. And I can't call it a curve anymore because it's two-dimensional. So I call it a surface. That's what a two-dimensional thing is. And since there are now three variables in play, x, y, and z, it's in three-dimensional space. So if I went w equals a function of x, y, and z, then we'll have a three-dimensional solid in four-dimensional space. Moreover, if we want to bring calculus into this, if I integrate a function f of x dx, I'm finding the area under the curve and above an interval on the x-axis. So if I integrate a function of two variables, I'm looking at what's under a two-dimensional surface in three-dimensional space. So I'm going to find the volume under the surface and above some region in the xy plane. We just push it up one dimension. At least when we get, so it's very simple to take our single variable calculus ideas and adapt them to a multivariable calculus environment. That last one does introduce an interesting thing. What makes integration of a single variable so simple is that we're integrating over an interval. The only subsets of the real numbers that we have to integrate over are intervals. The interval from a to b. That's the only thing that we have, unless there's an interval from a to b and then another interval from c to d, in which case we're doing two integrals anyway. But if we're integrating under a surface and above a region in the xy plane, the region in the xy plane could be lots of different shapes. It could be just a rectangle, an interval from a to b on the x and from c to d on the y, but it could be a circle where x and y are related. Or it could be some other funky shape like a piece of a parabola. Maybe this is the area over which we're integrating. But because we've learned our calculus, we do the same thing that we always do. Whatever shape it actually is in, we're going to assume that the surface is a constant height above the xy plane for a small change in x and a small change in y. We're still going to back up to volume to multiplication, and volume is length times width times height. Height will be determined by the function. Length and width will be small dx and dy. So we're going to break it up into rectangles anyway. That's Professor Leach's 5-Minute University. It's a cover of Father Guido Sarducci's 5-Minute University. Anyway, I got very distracted today, so we didn't do volumes of solids or revolution, but we did talk about what integration is about. We did talk about the restriction that we placed on ourselves when we chose the single variable calculus challenge. It's the single variable calculus challenge. Not all of you are going to be taking multivariable calculus, which is kind of a bummer because it really starts opening things up when you stop restricting yourself to just one variable. Looks like 5 ints. But it also forms a very complicated set of 5 units that you want to take. So if you don't need to take Calc 3, you should maybe you should avoid Calc 3. But if you're an engineer, you don't have any choice. So, any questions? Comments? Snide remarks? I love the question. I love that question. Question in the chat: why go to art school? Like, you go to art school because you love art, and that's what you want to do. And anytime you pick a major, and people in your family say, "Oh, what are you going to do with that major?" Make sure that they understand. If you say, "I'm going to be an art history major," or "I'm going to major in art," make sure that when someone questions you and say, "Well, what are you going to do with your art degree?" you remind them, you ask them, follow that up with this question. It's like, "Oh, so you're saying that if I go to art school, I don't deserve to have shelter or food or healthcare? Is that what you're asking?" Because that's what's implied in that question. That's what we need to start inferring from that question every time it comes up. And I don't care if it comes from your parents who are supposedly paying for you to go to school. They're either helping support you become an adult, or they're just being little dictators because you're their little vanity project. So stand up to it. Go to art school because you love it, and you feel compelled to do it. Any questions? Comments? Snide remarks? Hey, I said at the beginning, I'm going to try to talk you out of going to college because this is an enormous investment of money and also an enormous investment of time. The money, you could do things to get the money back, but time never comes back to you. So spend it wisely. That's going to do it for today. Everybody have a nice spring break. I hope you all do what I plan to do, which is get caught up on all the work that we don't have time for in our normal lives. And then, well, we probably shouldn't think about it too much. Let's just hope that we all get caught up, come back in a week, and are all energized to finish out the rest of the semester. All right, that's it for this week. Everybody have a nice spring break, and I will see you all the following Monday. Thanks for playing.